Recording is rolling. It is Thursday, February 8th. So plan for today is all these new posters hanging around my room for last week. You guys have thumbnail notes. I want to go through all those. Some will quick review of Thermo, and then some are new materials engineering type. Right. Well, we're gonna look last few minutes of class at some chapter 13 puzzles. So let me show you guys this right now, and just come back into class. Right. You guys remember earlier this week, chapter 12? We circled 6 of these and went through these, chapter 12, right? So on the opposite side of that same paper is chapter 13. We're going to do these 7. So in class today, we're just going to have a few minutes. So what I want to do is just go through and read each one, just so you guys are thinking about it. And then in the future, we'll go solve those one by one, right? But a lot of the posters that I want to go over today tell you exactly how to solve these 7 that I have circled, right? It's these 7 right here. And we'll just ignore the other 3, right? Also, we should have a couple spare minutes for, I know you guys are in the middle of registering for your next classes, right? So you guys are getting schedules together. Most of you guys probably have a paper that looks something like this. Now, this particular one is for 11th grade going into 12th, right? Which probably most of you guys have. Okay. Here, to get out of this one right here. I got some extra copies. Yeah. All right, so there's a place for a teacher's signature. If you need me to sign off, then yeah, you have an opportunity for that. All right, so you guys get what we're doing? All right, so let's switch over here and go through these posters. Poster time. All right, you guys ready to take some notes on these posters? Yeah. All right, so again, some of these are review like this one. You guys remember these 3 different temperature scales? Right, these are, now this one actually is like scale to scale, right? Absolute zeros down here, Kelvin scale. Right, here's some conversion formulas that also apply to those scales. This bottom one, guys, folks here. Right, this bottom one is how you convert from temperature in Celsius to temperature in Fahrenheit. We actually did do one of those example the other day. And this top one is how you go from temperature in Celsius to temperature in Kelvin, which you would have to do if you're ever given a temperature and you have to say like apply ideal gas law, for example, or entropy, or any equation where you could possibly scale up or down temperature by some factor, right? You have to have an absolute temperature, which has to be in Kelvin, okay? Right, so there you go. Now we get those. Laws of Thermo we went through the other day. The ones I care about in this class are just the first law and the second law. The other ones I'm not going to focus on so much, right? First law is basically conservation of energy. Second law is this one, remember you guys, has to do with the entropy increases as the universe moves forward in time, right? There's a certain time order of processes, right? Temperatures tend to reach equilibrium. You can stir milk into coffee. You can't stir it out, right? It's all related to that. Ooh, okay. Now here's one I haven't quite seen yet. Carnot cycle. So there are different thermodynamic cycles. This one's famous because I want to say this is like considered to be the most efficient of these thermodynamic cycles. Suppose you have, guys, look up here. Look up here. Suppose you have a cold sink and a hot sink. So there's a temperature differential, and you throw some kind of engine between that, right? You might be able to maybe like as thermal energy is moving from the hot to the cold sink, maybe expand and compress the gas, maybe like move a piston. So you can capture some of that energy and turn it into work, like mechanical energy that you could use to like drive different systems, right? Here's what the diagrams look like for that cycle. This is pressure versus volume. You notice these 2 curves. We're looking at the hot sink and the cold sink, so it could cycle around there. This bottom one's temperature versus entropy. You guys remember capital S represents entropy, right? And then it'll cycle like this. And I want to say the area embedded in those curves represents the work done, right? Say in joules, usually like that too, right? So it goes Carnot cycle. Here's a different thermodynamic cycle, Rankine cycle. This is how most electricity is generated, right? So now the exceptions real fast could be like solar energy could directly create electricity, but most electricity, like how do you get energy from coal or nuclear or petroleum, right? Or natural gas, right? Guys, most of the energy in this room, there's a lot of energy going on in this room. The lights, the air conditioning, the projection, right? Guys, most of that comes from what source? How about natural gas, right? And there's about 20% nuclear and maybe little percentages of other things, right? But how do you go from those sources to electricity, right? And it involves heating water to boil it, right? So we're going to boil some water. Now that steam, now we're going to use to turn a turbine, right? Okay, so there's some mechanical energy. right? So some of the number of joules of energy are now going to work turning the turbine. That's connected to a generator. We'll talk about generators a few weeks from now. All a generator is if you run a wire past a magnet, that generates an electric current, right? So now we're transferring the joules of energy onto electricity. So it takes that form. Oh, there's the grid right there. Then we can, that connects to, say, like this classroom. We can plug appliances in and make stuff happen. Right? Yay, fun. All right, let's go back to the cycle though. So now the steam leaves the turbine, and now it's been depleted of its useful energy, right? So you guys remember that entropy process, right? Right. So we're gonna condense it, take it back down to liquid form. Although maybe it's really hot water, maybe it's like 90 something degrees Celsius, right? And then pump it back around to the boiler. The fact that it's so hot means it's ready to be boiled again, right? Now you probably remember too, right? That you guys remember we solved a problem the other day, taking an ice cube and then melting it and then boiling it. So like, how much energy does that take, right? And most of the energy, most of that process actually went into the boiling process. So it takes a lot of energy to actually boil the water, right? Maybe that's why it's helpful that it starts off at a high temperature in the first place. Right? We're just pumping the same water through, so it's always hot. Right? It's always like 90 degrees Celsius or more, and then boil it, and so on. Right? So you guys go to the Rankine cycle, and there's temperature versus entropy, and the useful work in joules we're getting out of that. Yeah. Okay. Oh, Stirling engine. So the other day I played you guys at the end of class a Bill Nye video where you had one of these Stirling engines. I think do I have one up here on this demo shelf? I think I do. So I do. Yeah. All right. So it's like this right here. Here, I'll throw this here, and then here for the video, we switch over real fast. Boom. There's my Stirling engine. If you're watching the video, right? So go back over here. So there's a temperature differential, and then Bill Nye had like two different temperatures, right? They like hot water versus room temperature, or he had a vat of like ice water versus room temperature, right? So two different temperatures, temperature differential. You can get mechanical work, right? Here's pressure versus volume and temperature versus entropy for that type system, like Stirling cycle. Right. Oh, all right. So how efficient could any of these systems be? How do we define efficiency? So got a couple perspectives on here. You guys see this Greek letter eta, looks like an elongated N. That's Greek letter eta. We're going to use that to represent efficiency. Okay. Right. And here's maybe some general thermodynamic engine. So working off the temperature differential, hot sink, cold sink. Right. We got a heat transfer from hot to cold. Put an engine in the middle. Maybe we're able to like get a Stirling engine to move, for example. Right. And we're getting useful work out of that, which is also some number of joules. Right. Let me tag some numbers to this, for example. What if there's 100 joules of thermal energy leaves the hot sink and head toward the cold sink, right? 100 joules. And this engine is somehow able to capture like 30 of those joules and put that into mechanical energy, right? All right, so what this bottom box says is that we're going to take this 30 joules compared to the 100 joules transfer. Guys, what would the efficiency of that engine be? 30%, right? You guys see 30 over 100, that's 30%. There you go. Right? Which, by the way, is pretty close to your car efficiency. How efficient is your car at taking gasoline and turning into like mechanical energy, making the car go? Pretty close to 30%. Okay. Here's another perspective on efficiency. This is Carnot ideal efficiency. This is like if you want to max out, like theoretically, how efficient could a system possibly be, right? It goes like this: 1 minus the ratio of cold sink to hot sink temperatures, right? Now, here, let's do some examples again. Suppose your hot sink was like, 50 degrees Celsius, and your cold sink is like negative 10 degrees Celsius. Right? You guys got that? 50 degrees Celsius, negative 10 degrees Celsius. Can you over here in this formula go 50, negative 10, and run the numbers? Would that give you a correct answer to anything? No, because you have to do what to those numbers first? Convert to Kelvin, to make absolute. So add 273, 270. Okay, so something like that. Right now you can take a ratio. And then notice it's 1 minus that. Right, so I'm going to change some numbers again. Let's do another example. What if your cold sink is like absolute 0 Kelvin, and your hot sink is, I don't know, 300 Kelvin, just some number, right? Let's run the numbers. Guys, what is 0 divided by 300? 0. And 1 minus 0 is 1, right? And that could represent, in this case, 100% efficiency, right? Here, guys, everybody look here. Everybody think about this, right? So 100% efficiency. Now, you could never really truly have absolute 0. So it's kind of a theoretical case. we say is you can sort of asymptotically approach 100% efficiency, but you could never reach 100% efficiency, right? There's always going to be some increase in entropy. Right? Let's do the other boundary condition. What if your hot sink and cold sink match temperature? What if it's like 300 Kelvin and 300 Kelvin? Guys, what's 300 over 300? 1. What's 1 minus 1? 0. How efficient is that machine? 0. It's not doing anything at all, which makes sense, right? Like if you throw a Stirling engine here and there's no temperature differential, it's not even going to rotate, right? So how does this connect to what I want you guys to know before you graduate high school, right? When you guys graduate high school, you're going to go out probably to like 20 different things. Everybody's got different life going on, right? And at some point you're going to run it's like some version of math formulas in some way, right? How? I don't know. You're going to find out. But when you do, poke around with the formulas a little bit and see if you can find boundary conditions. See that it makes sense, right? In this case, we did that. You said that efficiency somewhere between 0 and 100%, right? It checks out, right? It makes sense, right? So even if you kind of forgot this, I bet you can kind of piece it back together. You say, how'd that efficiency go? Right? What kind of makes sense? I bet you can sort of logically figure this out, right? By learning it in school. Right. Oh, entropy. All right, so I think I want to add a little bit to this poster. Calls maybe like a hot sink and a cold sink, and there's an energy transfer or something like that, right? So the change in entropy, the increase or decrease in entropy. Say you had a hot sink and a cold sink and an energy transfer. Right. The cold sink is going to gain some thermal energy in joules, divide by the temperature. There's some increase in entropy, right? The hot sink is going to lose that exact same amount of energy, delta Q, right? But at a higher temperature. So the entropy goes down, but not as much as the entropy goes up for the cold sink. So that leads to the box on the right. The entropy from the point of view of the universe has to always increase with the passage of time. That's what this one says, right? That's the second law of thermo right there, right? Second law of thermo, right? We talked about that before, so that's a quick review, right? Right. Oh, you guys remember this? Water, pressure, temperature, phase diagram. Right. So different pressures, different temperatures. Right. Here's the 3 main phases that you see. Right. So you guys saw that the other day. Right. Now here's one particular slice. This could be at 1 atmosphere. Here, let me toggle back to the previous slide. Boom. Right. You guys see this red line, 1 atmosphere going across? Right. So, that's what we're sitting in this room right now, 1 atmosphere. Right. So is your increase in the temperature? Right. That's that slice right there. We're just looking at 1 atmosphere, just that one slice of that larger diagram, right? And we navigated this the other day. Here's when we're taking a ice cream from the freezer, we heat it up, melted, and then heat that up and boiled it away, and then kept heating it up. Say like, how much energy does that take, right? Notice, there's a lot of energy that goes in the boiling for water anyway, right? All right, Rankine cycle. All right, here's specific heat capacities for different materials. Notice water is pretty big compared to all these other materials. What does that mean? That means it's really hard to change the temperature of water, which is good news for us. Guys, what are you mostly made out of? Mostly what molecule are you made out of? Water. We're all about 2/3 water, right? And then other stuff. So guys, do we all have to maintain a stable body temperature? Right? If your temperature goes up by like 5 degrees, you get really, really sick, right? So, hey, the fact that water is so stable in its temperature, that helps us maintain our body temperature. A little side thought there. All right, Newton's law of cooling. Here's another thing Newton was interested in was what's the rate that something transfers thermal energy? It could cool down if you say have a hot cup of water, or the other way, if you have an ice cube, what's the rate that it melts? It could just be like this graph upside down. Right. And what this basically says is that the rate exchange of energy, that's what dq over dt is, right? It says what's the transfer of energy as a function of time, so energy per time. I think it's sort of like the slope of this curve, sort of like that, right? That is directly proportional to the difference in temperature. So you have a hot cup of water, leave it in room temperature for like 5 hours. Eventually it'll reach this environmental temperature, this room temperature. It's going to take a while for it to cool down. Cools down really fast at the beginning, and then slower until it reaches room temperature. There you go. Newton's law of cooling. All right, guys, get there? All right, states of matter. Here's 6 different states of matter, 6 different states. All right, so let's start with solids. Solids are considered to have constant volume and constant shape, basically, is what's going to make a solid, right? Right. Then, going on left-right axis, you could think is like colder to the left and hotter to the right. You guys think that, right? Although you could say too, you can make a case for changing pressure. You guys remember reduced pressure boiling, right? So it saw something like that too, right? But here, just kind of simplify. Let's keep it left cold, right hot. Okay. So what if you cool a solid more and more and more and get to close to absolute zero? Close to absolute zero. It'll actually undergo a really weird state change called Bose-Einstein condensate. Like those vibrating atoms at some point lose so much energy, they have trouble vibrating. And then they're no longer really individually atoms. They take this wave state called Bose-Einstein condensate. It's really weird. Okay, anyway, let's go the other way. Let's take a solid, maybe an ice cube, and heat it up until it melts and becomes a liquid. Okay, now what makes a liquid? So loose definition is a constant volume. Liquids usually are not really compressible, right? But not a definitive shape, right? So they'll just take whatever shape to fill a container, right? So heat that up until it boils. Now it makes a gas, right? What's a loose definition of a gas? Is something that has neither a definitive volume nor shape, right? So it'll basically occupy whatever container, and it is compressible, right? You can like compress a balloon, for example, something like that, right? Let's say you keep heating a gas. You might at some point finally strip away the electrons from the nuclei, right? That's a plasma. Guys, is there a plasma in this room? Look at fluorescent lights. Fluorescent lights. You guys think there's a long light bulb, has some gas in it, has some electricity running through it? Right. There's your plasma right there. Or how about stars? How about the sun? You guys think the sun's a giant ball of plasma? Right. And what if you keep heating? Do you think at some point those atoms can get so hot that it just tears apart the nuclei? Right. Maybe creates something called quark gluon plasma. Right. Now that's extremely hot. I think, I think you would really only kind of see that in maybe like a supernova explosion. Right? That's how we get like most of the elements in this room, right? There was like some supernova that happened, right? Created most of the elements in this room, except for like hydrogen. Right? And maybe the early universe, right? So like the first thousands of years after the Big Bang, maybe it was a bunch of this stuff, right? All right, there you go. You guys got on states of matter. All right, next one, density. So I'm going to use Greek letter rho. Looks like this curly P, Greek letter rho. That's going to be mass per unit volume. Okay, now that is a material property. So every material has some associated density. Oh, now why I got this crown submerged in this water. So this is a story with Archimedes. You guys know the story with Archimedes? Because all right. So that goes it. Maybe some of you guys know this. All right, and also not liar. So story goes way back in the day, Greece used to be a bunch of little city-states. There was one of these kings of these city-states was given this purportedly gold crown, but he had his suspicions. Like, I don't know, is this really gold or is it just some alloy mixed down, right? And he poses the question, how am I going to figure this out? And people can figure, well, okay, if we could know the density of the material, that could let us figure out, because we know gold has some density that's different than other metals, right? So mass per volume, right? But this crown is a weird shape. Like if it was a block, that would be convenient. You could just go length times width times height, get the volume, right? Throw the block on the scale, get the mass, divide the two, boom, you got your density, right? But what about like a weird shape like this, right? And so Archimedes thinking about this problem, and he's like, according to this legend, he's sitting down in this tub, and as he submerges himself down into the bath water, he notices the water level rise, and then it clicks. He says, "Oh, the level rise of the water is going to match however much volume I'm submerging, right? So that's how you can very quickly get the volume, even of a weird shape, right? And then according to this legend, he gets so excited about this, he jumps out of the bath and shouts Eureka, running through the street. There's a streak, and I guess he forgot to dress himself, right? Yeah, things you could do back in the ancient days. Oh yeah, good old innocent times. And then yeah, so they're able to run this problem with the crown and realize, oh, actually, it's not pure gold. It's like some alloy, right? But even today, scientists use this exact method to figure out what's some density of some weird object. So say you find some weird rock in your yard, like, hey, is this this looks like an asteroid. I wonder if this is a little meteoroid, right? Maybe it'd be mostly iron if it was. So you can run this exact experiment, right? And then figure out what's the density of your like weird rock. All right, ideal gas law. Okay, now this you saw the other day, so quick recap. Pressure, volume, absolute temperature, right? That's the main three variables I'm looking at. Pressure, volume, and temperature, right? Are related with that ideal gas law. What else I got here? Number of moles of gas is N, and R is just some constant to tie everything together, which has to do with what units you're working with. Is pressure in pascals or PSI? Is volume in liters or cubic meters, right? That's different values of R for all those. Okay. Right, then Archimedes principle. You guys remember yesterday, played you guys a bunch of Paul Hewitt demos. This was one of them. This one of he did. Right? You guys remember he took a weight, suspended it from a scale, suppose it was like 10 newtons, and he dunked it in water, and the scale reading went down. Right? And then however much water was displacing, he captured in a separate container, and he weighed that. And the weight of water displaced exactly matched the decrease in the reading on the scale from submerging it, because there's a buoyant force. So here, put it all together. What we're saying then is that the buoyant force, like that upward force if you're swimming around in the pool, is equal to the weight of the fluid displaced. Notice it's not the weight of the object itself, it's the weight of the displaced fluid, the weight of the water in this case, right? Right. And then you can break that down further. I know weight is mass times gravity. Remember that from last semester, right? And then mass is, well, that's density times volume, right? So now we got an expression for buoyant force in terms of the weight of the fluid that you're like swimming around in, right? The volume that's submerged, right? And then gravity field of the planet. We're going to use that to solve for. Here, I'll tell you one of the questions we'll solve is like how much of an iceberg is submerged? Right? You see an iceberg floating in the ocean. How much is submerged? It's going to be one of the ways we're going to solve it. Right? Pascal's principle. So this basically says pressure is transmitted and diminished. I think like I have a hydraulic lift here. Do you guys see this hydraulic lift? This hydraulic fluid in yellow, basically same pressure everywhere, right? Same pressure, right? Maybe you can make a case if you go deeper, slightly different. The pressure is the same on the left as it is on the right, right? Now, if the pressure is the same, and I remember from last semester, do you guys remember pressure is force per unit area? You guys remember that, right? So that means, okay, the ratio of force to area is the same on both sides, right? But if you have mismatching areas, that means you have mismatching forces, right? Because the ratio of force to area is the same, right? So with a small input force acting on a small cross-sectional area, that's going to deliver some pressure, which is going to transmit, which could, on a large cross-sectional area, lift a large weight, like a car you could do, right? There you go. You got hydraulic lift. Hydraulic press is basically same principle, something like that. Hey, does this remind you of like getting a mechanical advantage? You guys remember? Ooh, I have a pulley system right here. You guys remember building pulleys last semester, right? And you get a mechanical advantage from that. You could lift something that was heavy that you couldn't otherwise lift, right? Get a mechanical advantage, right? But the catch was with the pulley system, you had to pull lots and lots of rope. There's not pull lots and lots of rope, and then the heavy weight lifts up just a little bit at a time, right? Similar story with this car here. So with a small input force, yeah, you can lift something really heavy. The catch is you have to push down a long distance, and the car only lifts a little bit at a time, right? Because I guess the volumes of this hydraulic fluid displaced would be the same on both sides too, right? You displace 1 cubic meter on the left, you get 1 cubic meter on the right. Okay, guess that, and then divide by a large cross-sectional area, it moves up just a little bit, right? So there you go, mechanical advantage you get with the hydraulic lift. Right. Conservation of flow. You guys see this pipe system with some water flowing through it? You know, the next few slides are all going to go together. Right. So this is the beginning step of it. Right. So let's say you have water flowing from a large pipe into a small pipe. Right. Now it's going to be forced to change its speed because of this conservation principle. Right. Do you guys think this pipe system has the same gallons per minute running everywhere through it? Same gallons per minute, right? Right. Now that's like American units, but the metric unit could be cubic meter per second. The same idea, right? Right. It's the same everywhere. That's conservation of flow, right? Now I'm going to make the claim here that cross-sectional area times velocity is the same thing, right? Let's go look at this gold box down here, guys. Everybody look at this gold box down here, right? Right. So this is for incompressible fluid, say like liquids like water, for example. You can press on water and it doesn't really change its volume, right? So cross-sectional area times velocity should be conserved. Let's look at this in terms of units. Guys, cross-sectional area, is that like square meters? Velocity, is that meters per second? Put it all together. Is that cubic meters per second? That's like a flow rate, and that has to be the same everywhere in the pipe system. So A times V is the same everywhere, right? Guys see that? So suppose this A2 is half of this A1. Just making some up. Suppose A2 is half of A1. What is V2 compared to V1? Twice as much. It's going twice as fast, right? Half the cross-sectional area is twice the speed, right? 1/3 of the cross-sectional area is 3 times the speed. You guys see it too, right? Right. All right. Now, what if we go one step more complicated? What if it's a compressible fluid like air, right? What if you're blowing air through this? Well, okay, now that might have a density change, So I threw in rho for density. Okay. In this class, don't worry about the green box so much. We're going to mostly focus on this yellow box. Okay. Right. Okay. Now that's the setup for this next slide. Bernoulli principle. All right. You guys ready for Bernoulli principle? All right. Let me do a. Wait, is this the one? Yeah. Okay. I'm gonna do a demo for you guys. I got this paper. You guys see this paper? All right. So if you watch this video, maybe use your imagination. I got this. Oh, actually, I need to just put on the camera. Maybe I do that. All right. So I'm gonna blow a stream of air across the top of this paper. Blow a stream of air, and I want you guys to predict. You guys, tell me if I blow a stream of air across the top, is that gonna push the paper down, or is it gonna vacuum it up? Let's see. Show hands. How many guys say vacuum up? Vacuum up. Ooh, let's. Ooh. I think I have a bunch of winners here. Let's see. It does vacuum up, right? So what you guys just saw is science. You guys saw a moving fluid creates a decreased pressure. That's what you just saw, right? Right. That's what. Okay, back to this presentation here. Oh, I forgot to. Here. Whoops. Sorry, if you're watching the video, I forgot to show that. I forgot to switch the screen. Let me do it one more time again. There you go. Blowing a stream of air across the top causes it to lift. You guys saw decreased. Okay, so you see back over here. All right, so flip back over to this presentation. Okay, so here's the equation for that, and I want you guys to see where this equation comes from. Okay, so I have 6 terms: boink, 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 boink. You guys see 6 terms, right? If you kind of stand back and stare at it, it kind of looks like conservation of energy, right? There's going to be some energy. We got mgh potential energy, got 1/2 mv squared kinetic energy. You guys see that, right? Hey, what if you take each one of these 6 terms and you divide by a volume term, right? Turns out energy divided by volume gives you a pressure unit in pascals. So I'll call it like some internal pressure. Now, I got a story here with a fish swimming through a pipe system. You guys think that fish feels some pressure on them? You guys think? Right? So think of this like the internal pressure of the water there. Ooh, right? Then, so mgh could be potential energy. Because what is mass divided by volume? What is that? Is that density, right? Mass per volume. Hey, that's this Greek letter rho right here. Rho gh, and the same thing for the kinetic energy term turns into 1/2 rho v squared. You guys see this come together? So this Bernoulli principle is basically conservation of energy. Just divide everything by volume to get it in pressure units. That's it. Right? Guys, it? All right. So let's go to this fish then. Let's follow this fish story. Do you guys think this fish feels changing pressures going through this pipe system? Right? Definitely the height change. But yeah, I mean, you guys all been in a swimming pool, right? You dive deep down, feel the pressure go up, go to the surface, feel the pressure decrease, right? Right. But also because of a speed change. You just saw that with like blowing over the top of the paper, right? All right, so that would count too. Let's do a speed change. Let me flip back to this one, right? Let's say we get rid of a height change. Are you guys good with this? Just a horizontal flow, horizontal pipe, right? Right. Let's try this. What if the okay, so if we're just thinking horizontally, let's ignore the brown terms. Can you guys ignore these 2 brown terms? Right. So just to boil this down to a horizontal pipe system, I got the blue, green, blue, green. You guys see that? Right. Let's think what's going to happen to the pressure on this fish as it goes from the big pipe to the little pipe. Hey guys, going from the big pipe to the little pipe, does the water speed up? Speeds up, right? Okay. Now I'm going to create some numbers, just throw them in here. Let's say this internal pressure P was like 10 units. You guys got 10 units, right? And it's 1/2 rho v squared also was like 10 units, right? I don't know, pascals or something, right? Right. And then switch over to the right side of the equation. The fact that the water speeds up, do you guys think this new green term is more than 10 units, right? Because this V2 is bigger than this V1, right? Maybe it's like 15 units, right? Guys, what's 10 plus 10 on the left? What's 10 plus 10? Is that 20? Right. Now on the right side, if I call this green term now 15 units, that leaves how many units of pressure for this P? What's, you guys said 10 plus 10 is 20, right? Yeah. Okay. Minus this 15 gives you 5. So this fish experiences 10 units of pressure on the left, but only 5 units of pressure by the time it gets to the small pipe, right? That's even ignoring the height change. That has nothing to do with the height change, right? Right, set? Right. So, and that's exactly what you guys just saw with the like going across the top of paper, right? So moving fluids decrease pressure. Right? Try that too. When you guys say like turn on the shower head and you have the shower curtain might vacuum in, right? You might get something like that. Right? Say that too. Bernoulli principle. Right? Venturi effect. This is also Bernoulli principle. It's just a specific application. Suppose you have two different fluids that don't mix, maybe oil and water, for example, or water and mercury. Just two fluids that don't mix. Right? Uh, now, going from the small pipe to the big pipe, we just ran some numbers and said it's got to decrease pressure, right? So concentration of flow, it speeds up, and because it speeds up, Bernoulli principle, it decreases pressure, and that's exactly reflected in this height change. So I have a large density fluid here. Okay, so you guys see how it's like getting vacuumed up. Guess that. And here's the math for that. Again, it's just kind of Bernoulli principle, just rearranged, right? Right, you guys good? All right. Let's do some engineering. Stress and strain. Stress and strain. Okay, so what is stress and what is strain? Right. So stress, using Greek letter sigma, and I'm saying it's force per unit area. Oh, force per area. Is that pressure? Is that just pressure? Right. Stress is just pressure, but just applied to solids. Right. So over here, I got a picture of maybe a cross section of some column or beam or something, right? And here I'm showing a tensile stress. So I'm pulling with like a tensile force divided by a cross-sectional area, there's some tensile stress, right? You could reverse that and make a compressive stress too, right? Just reverse the forces, right? And this whole thing would also apply, right? So, but I'm showing it tensile so I can show this stretching out. And there's some delta L, some change in length. Okay, so now I'm getting at the idea of strain, and this is Greek letter epsilon, which is basically what percent does it change its length. So strain might be 1%, 2%, 3%, right? In response to some stress. A stress causes a strain for material properties. You guys get that? Right? So put it all together on this diagram. I got a stress strain diagram. And during this elastic portion, there's a linear relationship. And the slope of that line is called Young's modulus. That's a material property. So different materials will stretch or compress differently due to some stress, right? Like if you have a concrete block, I bet it's really brittle, probably barely changes at all, right? So there's some Young's modulus associated with concrete. It would be a very large value, right? Versus, what if you had like a sponge? You put a little stress on the sponge, you go squash real easy, right? And then let it go. It goes back to its original shape. So I bet a sponge has a very shallow slope for Young's modulus, right? The sponge could be like down here. Concrete could be like up here, right? You guys get that? Right? And then steel, I bet is okay, something like that, right? Okay, so that elastic zone will continue until it doesn't. It reaches this yield strength. Right. Now, as long as you're in the elastic zone, if you take the stress off, it just goes back to its original shape. But once you go past this yield strength, you go into permanent deformation. Right? In fact, for concrete, it just busts right there. Concrete is pretty much only compressible. And then once you hit the yield strength, it'll rupture. Right. But if you have a metal like steel, you might get some additional strain out of that. And you might even get an ultimate strength that's even greater than the yield strength until it'll rupture way over here. If you guys go the engineering route in college, you're going to see this graph all over the place. And if you don't, maybe you got a little appreciation for civil engineering, right? How these structures go together, right? All right. How about thermal expansion? How much does something change its length, say like strain, due to temperature change, right? So this says, here, let's read the music of this equation. The change in length is equal to the original length times, I'm going to skip over to delta T is the change in temperature, maybe like a temperature rise, right? Temperature rise, materials usually expand, right? And then what is this alpha? Is called the coefficient of thermal expansion. Now that's a material property. Again, kind of like Young's modulus, different materials will expand differently with, in this case, different temperatures or some given temperature change, right? Yeah, right. Right. So you guys got that? Check out. All right. Now hold on to the idea because that I'm going to come back to this idea later. The coefficient of thermal expansion, right? So hold on to the idea. Come back later. All right, I-beam. So you see this all over the place in construction. Why? What's the use of that shape? Why did it make that I shape? Right. So let's switch over here. I'm going to save a little bit of time and find. Oh, I thought I had a. Here we are. Right. So I pre-drew this here. Right. You guys see my I-beam? You guys see the I-beam in black ink right there? All right. Now let's suppose that this I-beam is resting on a couple of supports. So upward force it's resting on. And somebody's like walking around the top. So there's like a downward force right there. You guys see that? Is that going to bend this I-beam? Kind of like a smiley face. You guys see that? See a smiley face? Ever see that? Right. Maybe if you have a sponge, it would definitely look like that. So in green ink, kind of an exaggerated version of that. Now, guys, which line is longer? the top of this or the bottom? Which line is longer, the top or the bottom? The bottom, definitely, right? And that tells you something about the stress, right? Which is to say that the bottom's going to go into tension and the top's going to go into compression, right? So maybe you're like walking around a parking garage and you look up and you see the floor above you and you see like little cracks in the floor. Ooh, because it's starting to bend and go into tension, right? By the way, concrete has very little tensile strength. Concrete's really good at compression, but terrible at tension, right? Which I'm about to talk about later too. But here, let's stick to I-beams for now. So I-beams, right? So if it's compression on the top and tension in the bottom, do you think that somewhere in the middle it transitions and there's zero stress, right? That's this nodal line that I dashed off. Do you guys see this nodal line I dashed off right there, right? So that's okay. And if it's no stress, there's going to be no strain. You don't really need a lot of material. That's why this middle part of the I-beam, you don't need a lot of material, right? But you do need a lot of material where there's a lot of a lot of compression, a lot of tension. That's the top and bottom flanges, right? You guys see that too, right? So this I-beam is a engineering solution to where do you get the most stress and strain, right? But it's also an economic solution because steel is more expensive than concrete. What you might do is like lay down this I-beam and then possibly embed it in concrete. So you got different materials going on, right? And yeah, you're able to handle maximum stress. Right? Right. Speaking of concrete, give you guys a story of concrete. So 2,000 some years ago, Romans had concrete. They actually had a different version of concrete than we do today. Actually, I think it was arguably more durable than ours today. Like there are a lot of structures that still, like 2,000 years later, are still standing. And Romans built all kind of cool stuff with their concrete. They did, you could build stuff underwater. They got anything vertical, aqueducts. We got bridges. Got domes, right? But there was one thing that Romans could not figure out how to build. Actually, I'm getting a little ahead of myself. Right? Here, we'll go back to that. Hold on to that idea. Right? Well, let's look at modern day concrete because Roman Empire fell for almost 2,000 years. It was lost to history as to how do you make concrete at all. People saw all these structures, but they didn't know how to make them. And then I think it was around 1800s, another method of making concrete was discovered, and that's this one here. So you take Portland cement, a bunch of different sized rocks. Now here, this is simplified, but maybe you have large rocks, I'll call it coarse aggregate, and maybe like sand, could be fine aggregate, right? Mix that with a few add mixtures and water, and it'll undergo a chemical process. So concrete, really strong compressive strength, high compressive strength, relatively cheap compared to a lot of other materials. And then when you pour it, it's in liquid form, but then it cures and undergoes this chemical reaction, which is exothermic. Right? So the water doesn't evaporate. It doesn't dry out. Right? The water actually is part of a chemical reaction process, right? And then it'll solidify, it'll cure. Right? There you go. Okay, now let's get to this. Steel reinforced concrete. Right. So remember, I was saying there was one thing that the Romans did not know how to build, right? And that was second floors. Guys, are we sitting on the second floor right now? There's a whole classroom beneath us, isn't there? Right? Romans could not build that. They could not figure out how to do that. Right. So eventually, about 100 some years ago, a guy figures out, hey, if you embed some steel rebar, then you can build a second floor out of concrete, because now it's not just concrete, it's really a composite material. The concrete can handle compression all day long, but it has almost no tensile strength. If you pull on concrete, they'll pop apart real easy. But steel, ooh, not so much. Guys, look at the tensile strength of steel. Ooh, 50,000 psi or 345 megapascals, right? That's really strong, right? So now composite material, you can handle the compression, you can handle the tension, put it together, steel reinforced concrete. Now you can build second floors, right? But you know what else? Right? Let me just go back. You guys remember this right here, coefficient of thermal expansion? I said it was come back later, right? So what if, guys, think about this. What about between day and night or summer and winter? What if, guys, everybody think about this. I want you guys to think deeply about this. Guys, phones away. Guys, phones away. Everybody think about this, right? What if these different materials expanded at different rates in different temperatures in different seasons? Would this crack apart real easy, just fall apart, right? Which would be bad, right? Because now all our structures are falling apart, right? It turns out, by complete luck and coincidence of the universe, that both steel and concrete pretty much have the same coefficient of thermal expansion. Right? Now, there's different kind of concrete, different kind of steel, so there's a window of values, but they overlap. So that from season to season and from day to night, different temperatures and different conditions, right? these two different materials will actually expand and contract together, right? Which is really lucky, because now we can build all kind of cool stuff out of steel reinforced concrete. We can actually have this as a material, right? Composite material, right? And finally, catenary chain, catenary arch. If you hold either a chain or a rope or a string at the two ends, it'll naturally create a certain shape. People trying to figure out what is that shape for a long time. Is it a parabola? It's not quite a parabola. It's called a catenary. And nature is sort of telling us something about how that string or that chain wants to hang in equilibrium. Now, if you stiffen that and turn it upside down, you can create the arch version of that. And that is the strongest arch that you can possibly create for some confined space. So suppose you have like a doorway that's like, well, I don't know, like 10 feet wide, 14 feet high. We need an arch to like maximize the strength of this opening. What shape should we create? Well, you can stretch this catenary arch until it fits that shape. And that's like the strongest archway that you can create. Okay. So there's a little trivia. Well, that trivia right there. Switch over, and I promised you guys at the beginning class, we're going to just read these questions for chapter 13. Yeah, so we got a few minutes here, just as a setup for future class. So number here's okay. So number 80, right? So just plant this idea, you guys can sleep on this. I got some piston with this cross-sectional area, some amount of gas with some volume and some pressure. By the way, the pressure on my paper is 1 atmosphere pressure, which we're sitting in right now. We're going to take a 60 kilogram mass, which also has some weight, and put it on top until it compresses the gas. Now, what's the new volume of the cylinder? Do you guys think this we could solve with ideal gas law? Do you guys think ideal gas law? Ooh, I bet we could. PV equals nRT. Hold on to that idea. Something to do with like force equilibrium, right? Hold on to the idea. We'll do that. Number 84, we're going to solve. We got some statuette weighs this much in air, but then you submerge in water and the apparent weight changes. Hey, does that sound like that Paul Hewitt experiment? And I had a poster for that, right? What material is that made out of? This kind of sounds like the Archimedes crown problem too, right? Now it's a little bit different. It's a little bit more mathematically involved, but there is only one material that would correspond to these numbers, right? What would that be? And everybody has a different paper and a different version. So it might be possibly any one of these materials. So it made lots of different versions, right? All right, we're going to skip 87. Let's go to number 90. Suppose density of salt water. Guys, what is the density of fresh water? Is it right? 1,000 kilogram per cubic meter. You say 1 kilogram per liter, right? That was the original definition of a kilogram. You guys remember back in 1790s in France to try and figure out, what should the properties, right? So exactly 1,000 kilogram per cubic meter is fresh water. Do you guys think salt water is a bit more dense, right? So, I see that right there. Density of salt water. Yep, it's denser than fresh water. Now, this also got ice, which turns out is less dense than liquid water, right? Which most materials don't do that, but going from liquid to solid. But ice does because it takes like a crystal structure, right? So there. Right, so how much of the iceberg is submerged? You guys think we can use Archimedes principle to solve that? Right, so hold on to that idea. We'll do that one. Someone did? Right, number 93. I got a steel bridge, and it's so long. And I got a hot day in August and a cold day, cold night in January. You guys think that bridge is expanding and contracting with the seasons, right? And temperatures, right? How much longer will it be? And that might be good to know if you're an engineer, because you want to know maybe like where our stress is on different parts of the system, right? Now I'm focused on the length of the bridge. We're just focused on linear expansion. Keep in mind it does expand in all 3 dimensions, but if it's like anything that's like a long rod, maybe or a long bridge in this case, maybe you're mostly interested in its length. Right? We're gonna skip 95, which does talk about the volume. It's a good one to think about, but we're gonna skip my mind. Right? Number 108, hydraulic lift. Do you guys think Pascal's principle right here? Right? So would input force to lift a really large weight, given also, right? I think that would be pretty straightforward. Pascal's principle, right? And this pipe here, these last 2 questions go hand in hand. Right? Oh, look, I got some water going through a pipe. Does the water speed up going through the small section? Is that conservation of flow? Right? So that's this question right here. And then there's a follow-up question. Now you have to get B1 right to get B2. Right? Even if I didn't ask you one, you'd have to solve that first anyway to answer this next question, which asked about pressure. As if you're a fish swimming around in this pipe system. Let's see if you guys follow this. You guys remember, going from the big pipe to the little pipe, do you feel an increase or a decrease in pressure? decrease. Right? You guys remember I was blowing a stream of air across the paper and it lifted, it vacuumed up. Right? Water has to speed up, therefore pressure decrease. Okay. So what does the pressure decrease to? Right. Oh, do you guys think we'll use Bernoulli principle? Solve this last one. So conservation of flow, Bernoulli principle. All right. So you guys good with all right. So there you go. All right. So think about those. Solve those in class. Soon for too long. All right. Oh, perfect. We got 2 minutes of class. So guys, any schedules you guys have, pull those out and I'll sign whatever you guys need signed. All right. That's a wrap on the recording. It's going on the Google Classroom.